CBT Nugget's Network Plus series, Physical Network Topologies. Well, although this nugget is entitled Physical Network Topologies, we're also going to combine here some logical network topologies along with this because, as we're going to find out, there's some overlap. And this is an important nugget because this really gets to the design of your local area and wide area network. This is going to be the underpinning for the types of Layer 2 and Layer 3 protocols you choose, as well as the design options into some of the physical characteristics, the cabling and the connector types that you're going to use as well. So let's talk about 6 different general categories of network topologies. We'll talk about bus topologies, star topologies, ring topologies, mesh and partial mesh topologies, point-to-point topologies, and point-to-multipoint. Now, in our discussion of topologies, we're going to start out first of all looking at physical topologies. The physical topology of a network refers to the physical layout of the devices and the subsequent cabling that you choose. Now, you have to match the appropriate physical topology to the type of cabling. And we talked about cabling in the previous nugget. Things like twisted pair, coaxial cable, fiber, and so on, that you're going to use in your network installation. So understanding the type of cabling used is important in understanding each type of physical topology. Now, there are really 3 primary categories of physical topologies. We're going to look at the bus topology first, but you've also got star topologies and ring topologies. Now, realize that just because a particular topology is physical bus in nature, for example, it can be logically something different. So in a bus topology, and we'll talk about early bus topologies. Early on, this cable here was what we called a thick net cable. And you literally had devices. This is a cable, let's say, in a law office, and I'll just use an example from my past. A law office, a thick cable running around through the law office, and you actually had the workstations or the nodes tapping into this cable with some type of vampire tap. And at both ends of this wire, you would have termination, because on this Ethernet here, you're using what's called carrier sense multiple access with collision detection. So each device on the bus is sensing the media. Multiple devices are attempting to access the media, and they're using a collision detection mechanism so that only one node is transmitting at a time. A broadcast, for example, sent to all the nodes would terminate on both ends to prevent a loop from occurring. So in early bus topologies, the computers and other network devices were cabled together in a line, and it was either a thick net or a coax cable. So that was a physical bus topology. It's also referred to as a linear bus, because all the devices are in a line and all devices receive the signal. Think about it like a bus line going through a city. And again, you've got a terminator at both ends of the line, making sure that the electrical signal is not bouncing back from the end of the wire that will cause errors on the network. Now, this is a physical bus, but you can also have a logical bus topology, and we'll talk about that in just a minute. Let's go on now to the physical star topology. Next is a physical star topology, which is also referred to as a hub and spoke topology because, well, you've got a single device, a central device at the center, and all the devices are connected to this central hub device. So all the devices transmit through this central point. This central point represents the hub, and it's a single point of failure. So when you install this topology, it looks like the spokes in a bicycle wheel. You've got a central connection point, like a hub, a switch, or a router, where all the cabling segments actually converge. Every device on the network is connected to the central device with its own cable. Now, a physical star topology actually costs more to implement than a physical bus topology, but the advantages of a star topology make it worth the cost. Every device is connected to the central device with its own wire, so that if that cable has a problem, only that one device is affected and the rest of the network remains operational. In a bus topology, one device can bring down the whole chain, and the whole network can follow with it. Almost every newly designed Ethernet local area network is going to have a physical star topology with typically a centralized dedicated access switch, with a switch port for every laptop, workstation, network printer, and any other hard-wired network device in that broadcast domain. Now you can also expand your star network. Let me show you. You can also have an extended star network where you expand the topology to give you more resilience. Here, we've really got a backbone of several core devices. And typically you have higher speed bandwidths between these core devices than you do between these access points. You may also have redundancy built in, creating like a full mesh that we'll talk about here in a minute as well. This is an expansion of the basic star to include additional network devices that connect to the main network devices. So we could consider this our backbone device, maybe a backbone router or multi-layer switch. And here we have layer 3 switches or distribution switches, and these can connect to access level switches, and these of course connect to independent devices. And this really maps very closely to kind of a 3-layer design model where you have the core layer, the distribution layer right here. The second layer is a distribution layer, kind of messy. And then out here we have what's called the access layer. And then the access layer actually connects to the nodes or the host, the workstations, the laptops, the departmental servers, the network printers, the plotters, the wireless access points, things like that. The third general category of physical topologies is the ring topology, and these became pretty popular with the monolithic early IBM networks and the token ring network. Now, as the name implies, in a ring topology, all of the devices on the network are connected in the form of a ring or a circle. And unlike the physical bus topology, a ring topology has no beginning or end that has to be terminated. And the data is transmitted in a way that's very different from the logical bus topology. In a token ring environment, a token, which I'll put right here, a token actually passes in counterclockwise order around the ring, stopping at every device. If a device wants to transmit data, it adds that data and the destination address to the token. The token then continues around the ring to the destination, which then takes the data out of the token. Now, the advantage to using this type of method is that there's no collision of data packets. So we don't use carrier sense multiple access collision detection. We actually use collision avoidance. So we don't have the kind of collisions that we have on an Ethernet bus environment. Now, there are two types of ring topology. The single ring, and as I showed you earlier how you can expand out the physical star, well, you can expand out the single ring to a dual ring. Now, in a single ring topology that we see here, all the devices on the network share a single cable, and the data travels in one direction only. Every device waits its turn to send data over the network. But the problem with the single ring is it's susceptible to a single failure. If the ring comes down, the entire ring stops functioning. Now, in a dual ring topology, you have two concentric rings allowing data to be sent in both directions. One ring counterclockwise and the other ring clockwise. This is going to give you redundancy or fault tolerance so that if one ring fails, data can be transmitted on the other ring. And all of the devices that operate in this dual ring scenario, all of these nodes, whether they be servers or workstations, have network interface cards that are compatible with this dual ring scenario. A very popular dual ring technology is called FDDI, FDDI, which is Fiber Distributed Data Interface. And this is a data transmission standard for local area networks that actually can extend up to 124 miles. You often see these used in storage area networks as well, or maybe a backbone for a metropolitan area network, because it can use fiber. Now, technically it's a token ring network, but it doesn't use the 802.5 token ring standard, okay? Ethernet's 802.3, with a lot of variations after the 3 token rings 802.5, well, FDDI actually uses 802.4 token bus timed token protocol, and it uses a dual attached counter-rotating token ring topology to provide built-in redundancy and fault tolerance. Now that we've talked about physical topologies, I want to talk about logical topologies. The logical topology of a network refers to the logical paths that the signals use to travel from one point on the network to another. In other words, it's the way in which data accesses the network media and transmits packets across that media. So the physical and logical topologies of a network can be the same. So you can have a star topology in the sense that here you've got let's say a switch. I'll make this an S. This is a switch, and you have these devices, let's say workstations, plugged in to individual ports on this switch. So it's a physical star, but it's also a logical star. When I showed you the bus topology of the kind of the old school where you had the coaxial or thick net cable running through the office and devices were tapped into that cable, that was a physical bus topology and a logical bus topology. In other words, the network has the same physical bus and logical bus, or physical star and logical star. However, your network can also have a physical and logical topology that's quite different. For example, our physical topology could be in the shape of a star, where all the devices connect to a central hub. Let me clean up this picture real quick. For example, if this device here in the middle is an Ethernet hub, okay? It's got ports on the front, but it's basically just a hub or a repeater. What's happening is it's physically set up in a star topology. All the devices connect into the hub, but in the back plane or internally on this hub, it's a bus. It's still shared Ethernet. They're sharing the same logical bus. So you can have a physical configuration of devices plugged into a central device. Physically it's a star, but it's still operating with a contention-based carrier sense multiple access collision detection Ethernet environment, like a bus topology in a logical fashion. In other words, the way that the data accesses the network media and the way that packets are transmitted across it. This could also be this device. This could also be what's called an MAU. An MAU is a special kind of hub that's used in token ring networks. So although the devices connect to this MAU, it's still using token ring. The ring is still being passed. Actually, it's going to be going the other direction. So it's still going to be going in counterclockwise direction. The ring is being passed from device to device to device. It looks like a star because all the devices connect to the MAU or the token ring hub, but the MAU is still passing the token around in counterclockwise fashion. So you've got a physical star topology, but you've got a logical ring topology. The same thing on a FDDI or a FDDI network. Okay, it may look like the hub, which is supporting the FDDI technology, it's configured in a star topology, but logically it's using a FDDI dual concentric ring for availability and reliability. And of course, any server that's connected, any device, has to have a special network interface card that supports that dual ring. And we haven't talked about wireless networking yet, but a wireless access point, let's say this is a wireless access point here, got a couple of antennae on it, and we have a bunch of laptops out here. Okay, a wireless access point is actually a hub. So you have all of these wireless devices contending for the available bandwidth in that area. So although it may look physically like something else, it's still logically using an Ethernet, shared Ethernet bus topology in that wireless access point. So it's important to understand that you can have a combination of different physical topologies and logical topologies. Yes, they may be the same in a fast Ethernet switched environment, or in the case of FDDI or token ring or wireless, or even an old school bunch of devices connected to a hub, maybe in your home, it's got a different physical and logical topology. Let's talk now about some different other types of topologies. Now, a full mesh topology is where all of the devices are connected to each other. All the nodes have a link to one another for redundancy and fault tolerance. Now, creating a fault-tolerant full mesh topology in a local area network is no big deal because everything is relatively close together. Where full mesh topology as a design issue comes into play in wide area networking. Now, we're going to talk later on in this Nugget series about wide area networking topologies and technologies in greater detail. But you need to understand that a full mesh topology is a physical topology that's highly fault tolerant. But for every new node you add, it has to connect to all the other nodes. So it's an expensive solution, expensive to implement. For an organization to create over a geographical area, let's say like metropolitan Phoenix, a full mesh topology for their business is an expensive venture. Now, there are new technologies out there that are making it more cost feasible. And if you think about it, with things like IP telephony, or voice over IP, where telephones are now using the packet switch network, you kind of have to have that full mesh topology to have a phone system for a company that spreads out over, let's say, well, metropolitan Phoenix. So it's expensive, but there are methods in place by providers and telecom companies that are bringing down the cost of creating a full mesh topology. But this is the most resilient topology. Any single link failing is not going to affect reachability. Now, because of the cost, there's been a trade-off of fault tolerance and cost by bringing in what's called a partial mesh topology. And a partial mesh topology basically says this. Let me go ahead and write in my heading here. Partial mesh. And this is what companies have historically done more often. They would say, well, this is the hub or the headquarters, and what we'll do is we'll create a full mesh environment between our most important regional branch offices or our most mission critical areas. So we might have a full mesh with certain nodes, but only a partial mesh or a partial mesh. This could be a mess as well. A partial mesh with, let's say, smaller branch offices or strategic partners or other extranet sites. So instead of creating the full mesh, we create a partial mesh, and we can have the less mission critical sites actually use the hub or the headquarters for most of its traffic, and maybe can have direct connection to one other part of the network. So the bottom line here is this: in a partial mesh topology, at least one device maintains multiple connections to all the other devices. And this would be, let's say, our headquarters router here, okay, without being fully meshed. This is a trade-off because it reduces the cost of meshing all the devices by allowing you as a network designer to decide which nodes are the most critical nodes and then appropriately interconnect those nodes. And again, full mesh and partial mesh really come into play in wide area networking design and metropolitan area networking design. Now, another decision that has to be made from a topological standpoint, specifically in wide area networking, is whether you're going to go with a point-to-point connection or a point-to-multipoint connection. And this usually relates to the routing protocol that you're using to share information across all of these different points in a wide area or metropolitan area network. If you're using OSPF or ISIS, or maybe you're using EIGRP or Border Gateway Protocol, okay? So in a point-to-point, for example, this is our hub or our headquarters. In a point-to-point scenario, this device, this network device, would have 5 independent physical interfaces, each one of these creating an individual point-to-point connection to these remote sites. So these might be on their own, each one of these on their own TCP/IP subnet with their own IP addressing scheme. And then, of course, the routing protocol has to handle these 5 different point-to-point links accordingly. So this is really an issue as far as what is the dynamic routing protocol you're using and what is the configuration preference of the network engineer. Point-to-point has been used historically and commonly for leased line connections. It's also used in frame relay connections, which we'll talk about later on, among others, over wide area and metropolitan area networks. Now I want to throw this tidbit in there. Let's say this is a Cisco router, okay? I'm going to use Cisco as my example because I'm a Cisco guy. This is a Cisco router, and I want to use point-to-point wide area network connections. Historically, with a Cisco router, I've got these options for my actual physical cabling choices that I can use, these different implementations. EIA TIA 232, EIA TIA 449, V35, X21, EIA 530. So I'm showing you this to say that even if we come down to the point where we're choosing a point-to-point wide area network solution with a partial mesh topology, I still have to think about what is the actual physical serial, okay? What is the physical serial point-to-point cabling I'm going to use for my solution? So I'm throwing this in there just to show you that, again, always with these topological choices, there's always physical choices that are going to be supporting these logical and physical topological choices. Next we have what's called point-to-multipoint. And let's say I only want to use a single cable. A single cable coming from my headquarters router, a single serial cable connecting to my internet provider here. What I can do is I can have a single interface, and I can have actually 5 sub-interfaces. So I have point to multipoint. Here's my point. Here's my multipoints. M1, M2, M3, M4. You get the picture here. So what actually happens is this. I have one physical interface using one of those cables, for example, I showed you earlier, or I can use other options as well. But one single interface, and then I have underneath these, let's say that's serial interface, serial 0, I can have sub-interfaces. I can have serial 0.1, which goes to M1, serial 0.2, sub-interface that goes to M2, and so on, .3, .4. And basically, I strip away any of the configuration on the actual physical serial interface, and all the configuration, all the policy, all the IP addressing and other features are configured on a sub-interface basis. Each of these sub-interfaces being a logical point-to-point to my 5 endpoints. But a point-to-multipoint takes a serial interface, a single interface, and it multiplexes it into multiple points of destinations or targets. That's also a popular technology and topology that's used with things, for example, like frame relay. Okay, well that wraps up our discussion of physical and logical topologies. Again, we'll revisit a lot of these things later on. We talk about, for example, wireless networking. We talk about wide area network technologies and so forth. Well, in this Network Plus Nugget, we talked about 6 key technologies or topologies. Physical and, of course, logical topologies. We looked at bus topologies, physical and logical star topologies, ring topologies and dual ring topologies, including token ring and FIDI. We looked at mesh and partial mesh. And then, of course, some wide area networking technology, point-to-point links, and point-to-multipoint topologies. I hope this CBT Nugget has been informative for you. I want to thank you for viewing. See you later.